Welcome to Data Secrets from a Platform Engineer by Dr. Rebecca Bilbro.
Thank you. Welcome, everyone. Thank you for coming to find out some secrets. I'm excited to spend 30 to 40 minutes with you. If you want to do questions, I've been told to do that out in the hall so that we can all be like in as narrow a corridor as possible. That's intentional. To build camaraderie. So if you end up leaving halfway through, I'm going to give you one secret. This is like a taster, which is when we sort of crossed the line into deploying Jupyter notebooks as production code, we at the data science community decided to become SREs. Because if you are deploying your Jupyter notebooks as code, you know, the boss is calling you on the weekend to ask why the pipeline failed, right? It's not, you know, some DevOps person, it's the data scientist, because you're the one who wrote the code, you deployed the notebook, it's your problem, right? So, but I think that, you know, I was really actually kind of surprised by the lineup of talks for this conference. I was here maybe 6 years ago when I was working on my last book, and spoiler, I'm going to talk about the new book that I'm working on. But when I was here the last time, the talks were all kind of like, here's a cool algorithm that I just learned how to use, here's my favorite Python library. But we're kind of like moving in a direction, I think, as a community towards like, not this cool thing I found, this cool thing I did, but like, I have to do this for work or else I am fired. And I think that like, that feels healthy to me, right? That means that we're becoming, we're taking ourselves a little bit more seriously, maybe we're taking our work a little bit more seriously, and I think that that's actually a good thing, even though it feels a little bit intense. So my name is Rebecca. I'm one of the co-creators of the scikit Yellowbrick library, which now I'm not sure if anybody uses because of AI, but you know, it's a long time ago. My co-author of the scikit Yellowbrick library is here, Dr. Benjamin Bencourt. So we wrote this about 10 years ago, and it became, you know, like one of the biggest machine learning libraries on the Python package index, and it's designed to basically like do a hybrid of the matplotlib API and the scikit-learn API, so that you can just kind of easily fit your model and then render a visualization quickly to say like, did I go in the right direction? Did I screw up my hyperparams? You know, just to kind of like make sure you were on the right track. So that was scikit Yellowbrick. And then I worked on two O'Reilly books. And so a little bit of kind of what I wanted to talk about today is like, how could two books be written by a single person? Like, how could you be interested in, on the one hand, NLP and data science and machine learning, and on the other hand, lake houses and platform engineering, because they feel like two super different things. But what I'm going to sort of take you through is sort of the trajectory of my journey of kind of going from somebody who would write the first book, who was thinking a lot about you know, the early days of language modeling, and to somebody now who's thinking more about platforms. Because I think that that is probably the journey that many of you are on also, which is why the conference this time is a lot more about data engineering and pipelines and like, how are we actually going to run this stuff into production and get stuff done. So I suspect that many of us kind of are on the same journey. So for me, this starts a long time ago with me asking myself this question: why are my queries taking so long? So at the time, I was still learning how to code. This was, you know, this was like 15 years ago maybe. I was learning how to code. I actually learned Python before I learned SQL. So for me, the easiest way to interact with a SQL database was through SQL Alchemy, or, you know, other kind of ORM type tools. That was just kind of like the easiest path for me. And I was like, okay, I have to write this data science code. It's going to do some visualization stuff, and I'm going to read from this database. I'm going to write it in Python because that'll be way faster for me. And so I did, and it was great, and I demoed it. But then, like, the amount of data that I had to show, you know, because they kept asking for new features and new crosstabs and stuff like that. So the columns started to get bigger, and like the rows started to increase. and my queries started to get slower and slower. And I was like, what the heck is going on? And so I actually got curious, and I looked into ORMs, and I learned a little bit more about how they work, and I realized that if I rewrote my SQL Alchemy code in pure SQL, I went from queries that took like 8 hours to run to like minutes, right? So like that was a huge like mind-blowing thing for me, that somehow, you know, kind of the difference between using something that felt easy to me to doing something that felt harder to me but was easier for the database actually ended up being better for me. So I think that that's sort of like probably for a lot of people when you start walking down this path towards the platform, like towards data, towards more engineering, it's because you experience something like this and you have kind of a wake-up call where it's like, oh, I'm doing things in a dumb way and I could easily do it in a smarter way. So one of the things that I used to work on a lot, and actually I still do, is entity resolution. You know, so entity resolution, you got a bunch of references, different data sets, you're trying to figure out which things are referring to the same, you know, core entities. You can't really do this without doing pairwise comparisons, which sucks, especially on strings, because it's really slow. And so, you know, I would write code kind of like this. And it's like a little embarrassing to show code that you wrote that long ago, but don't look at it too close. But you know, it's kind of this sort of logic pattern where it's like, okay, you know, I've got kind of these batches, I'm gonna do this in batches, and I've got sort of this clever idea that I can do entity resolution in batches, right? Because I don't need to do all of the resolution all at once. I can just compare pairs in batches over time, and over time, the system will eventually accumulate resolved references, right? So I thought this was a really cool idea. And the way that I was gonna do it is I was gonna exploit the fact that every reference, I could assign it a unique identifier. In fact, I could just get that unique identifier from the database because I'm used to, now I know how to write SQL. So now I can, you know, kind of get these unique identifiers for each reference. And then I can compare two references, and whichever of those two has the smallest unique ID, I will make that the canonical representative. And you can just keep doing that in batches forever. But in order to do that, you actually need to be working on a database, which it turned out in this case I was not. I was working in a warehouse because warehouses had just been invented. And with warehouses, there was no guarantee of having that globally unique identifier handed out by the database. And like, this seemed very confusing to me. It's like, why? That seems like a fairly obvious feature that you'd want to give. Why wouldn't you give out a unique identifier generator? That seems like low-hanging fruit, table stakes for databases. Why wouldn't you do this for a data warehouse? They're supposed to be all new and fancy, and they're supposed to be great. But this is sort of like when I start to go deeper into the rabbit hole that has landed me now almost like fairly confident to call myself a platform engineer. I'm not sure if I'm 100% confident calling myself that now, but you know, this is sort of the beginnings of that. You know, and so what I did is I started to dig into, okay, well, what actually is the difference between a database and a warehouse? Because I feel like now I need to know that because it's going to impact like the data science code I'm going to write. Like I can't do entity resolution the way I thought I could because I can't depend on this sort of like fundamental thing that I thought was going to be really fast and easy to do. Because I mean, if I generate my own, you know, GUID generator, I'm going to do it in Python, it's going to be slow. It's going to slow everything down. Sort of like defeats the purpose in the first place, right? And so, you know, probably most of you have discovered these lessons now. But, you know, a warehouse is designed to give you like the database experience, but it's not a database. You know, it's actually a bunch of columns that just get like glued together when you ask for them. So it takes a column here, column B, column C, and like glues them all together and then returns like a materialized view to you, but it's not a real database. So it can't actually do the things that databases do, like true transactions, true upserts, true deletes. It can't do those kinds of things. Warehouses are changing all the time, so fact check me if you know you're using an amazing warehouse now that has added some kind of magic features. But I think for a lot of people, you probably had, if you were kind of following along in this journey in real time when warehouses were first, you know, released onto the market, you maybe had like a similar moment where you're like, what can I depend on now? What do I know to be true? So the next thing that I started working on, from kind of the entity resolution path was kind of going down this path of becoming an NLP specialist, natural language processing, not neuro-linguistic programming, but natural language processing specialist, and worked on a book called Applied Text Analysis with Python. Basically the idea was to kind of try to expose all of the work that you have to do on your documents, on your corpus, in order to get it ready to send it to the LLM. So most of the work that you have to do is right here, right? So most of the work is taking the documents, breaking them down in paragraphs, taking the paragraphs, breaking them down in sentences, taking the sentences, breaking them down into tokens, and then deciding if the tokens are like what their part of speech is, right? So you end up with lists of tuples, and then those lists are lists of lists, and then those lists are lists of lists of lists. So you end up with a structure, and you have to do that pre-processing periodically, right? You can't just do all this pre-processing and then throw away the raw corpus, because what if you did it wrong, which happens, right? So you need to store the raw corpus somehow. But one of the things that I realized as I was working on the applied text analysis book is I was repeating this a lot more than was strictly necessary, right? Because when you're tuning an LLM, like the stuff that you're tuning is like maybe, hyperparameters, right? Like you're not tuning the tagger each time. Probably, maybe you change that rarely. Maybe you find a bug somewhere in your tokenizer and you go and fix that periodically, but it's not something that you have to do on each training run. Right, and that was, I think, another kind of big realization for me. Like, I need to understand the underlying data better so that I can be smarter about how I'm building my machine learning pipelines. So around the same time, this is not from me, but this is something that I actually referenced when it was published. This is, somebody posting a GitHub issue for the SageMaker Python SDK, and it's a very nice message. It follows all of the rules, all the things you're supposed to do. You give examples, you provide a full stack trace, you don't act like a jerk. So it did all the right things, right? And so basically this person is saying, every 9 days our pipeline mysteriously fails because it can't find the data, even though we know the data is there. What is going on? And I think they're still waiting for a response, but here, like that is what takes you down the rabbit hole. Like you wait for a response long enough that you're like, I'm getting fired before I'm getting a response. So I need to find out what the answer is. Why is this happening, right? And you have to become a data engineer or a cloud engineer or maybe a platform engineer. You have to start to kind of dip your toes in those waters in order to figure this stuff out, because the information is insufficient, right? So this last line says, it is very difficult to debug as we cannot add log lines to figure out what is happening. And that is the fundamental problem, right? When you are a user of the platform, you cannot find out what's going on because that information is abstracted away from you intentionally, to try to make you more productive, to, try to, remove some of the concerns that you normally would have so you can focus on the algorithms and the hyperparams and all that stuff. So deeper down the rabbit hole I fell. So I was like, what could cause something to intermittently fail or potentially routinely fail every 9 days? How is it possible that an S3 bucket that you expect to be there, or a node that you expect to be there, suddenly wouldn't be there, and it would cause all of your machine learning training code to fail in the middle of maybe a very long training cycle that's been going for a while, and you were really invested in it being successful, and now it's failed, and you have to start all over again. Potentially that's happened to some of you before. And so I started to learn. I actually ended up taking a graduate level distributed systems class at the University of Maryland because I fell really far down that rabbit hole because I really wanted to understand. And here are some of the things that I learned that I think that you might know on some level, but maybe haven't fully kind of interrogated how this is related to some of the weird intermittent failures and challenges that you experience as you are trying to build on top of platforms, either platforms that your organization has built for you, or maybe one that you're using, that your company has subscribed to or something. So this is, what you are interacting with is not a single computer. You're interacting always with a distributed system, right? And that distributed system is a bunch of computers that work together and pretend like they're one computer, but they're not. And that's actually the cause of a lot of the weird stuff that you see, right? Like nodes going down, things being unavailable, data being different when you kind of query it once and then you query it next and you get different answers. A lot of that comes down to the fact that there is a system that's pretending to be one computer, but it's actually many computers that are having to talk to each other and work together. Now that sounds kind of bad. Like, why would we make it harder? Well, I mean, it's mostly good. You just don't always appreciate why it's so good. So one of the main things is that if you've got kind of this group of peers that are working together, they can have each other's back if something goes wrong. So if we have users who are connecting to our single web application or a single platform from across the world, and there's a devastating earthquake in one region, is all of our data going to be gone? No, because there's copies. So there's copies, so the peers all have copies of the data. So they are safeguarding kind of a copy, which is great. We store those copies on different continents, and that gives us kind of that sense of safety and security, that even if something really catastrophic happens, we're not going to lose all of our bank data or all of our healthcare data, right? There's backups. The other thing is that it's good for UX. And so every time you go to a website and you experience good UX, and you're, let's say, I don't know, this probably hasn't happened to anybody recently, but if you go and buy, let's say, like an airplane ticket, and it happens fast, and you don't wait, and there's no delays, and it's just like really quick, like the reason that happened is because of availability, right? It's because one of the peers is probably co-located with you. Like you are physically close to one of the peers, and so it returns answers faster to you, because like latency is actually related to geographic distance. So if you are actually physically co-located with one of the peers, you're going to have better user experience. This also explains, like, if you are working with a team on another continent and there aren't enough copies, this explains why they might experience a huge amount of latency for some of their queries, even though you are running the exact same queries and having the answer come back quick. It's because of like actual physical geographic distance. So having copies allows the system to feel more available to users. It's good for UX. But copies cause problems. So let's say we've got two different users. We've got this user who's going to interact with alpha and say, I want you to set the key k to value v. And at the same time, and I'm saying at the same time in a special way because of distributed systems reasons, but at the same time, another totally different user talks to a different copy, a different peer, and says, you know what, could you set k to q? And those two things happen at the same time. And so then what you end up with is a system that gives one user one answer and another user another answer when they ask what the value of k is. And that seems bad, right? That seems like that could cause some problems. So peers can cause problems too, because now they're inconsistent, and we have to figure out some way to make them consistent. And as you can probably guess, making them consistent costs money. And so, a lot of the systems that we use, tools that we're using, like warehouse type tools, and a lot of the data platforming tools that we use, sort of kind of make tricksy use of availability, and they sort of don't deal with kind of making sure everything is exactly consistent all the time, because in reality, you're gonna buy that airplane ticket regardless, right? You want the airplane ticket, you're gonna buy it, And if, at the same time somebody else buys that exact same airplane ticket, how is the airline going to deal with it? After you show up with your suitcase, they're just gonna be like, oh, sorry, you're in the wrong seat. We're gonna put you in this other seat, right? So they're just gonna act like nothing happened. They're just gonna absorb the failure, right? They're not dealing with the consistency on a systems level. They're dealing with it, sort of a customer, service level, right? So they can get away with that and save money. Okay. So the next thing I think that was really critical to my journey down this rabbit hole was the gradual recognition that started to dawn on me that very few people seemed like they were getting their models actually to production. So I told you, like the last time I was here at PyData NYC, people were talking a big game. They were talking about all these cool classifiers that they were writing and all of their sentiment analysis stuff. But when you kind of really talk to somebody one-on-one, what you got was like, oh, well, we finished the prototype. And like, there's a bunch of kind of like dog whistle type words that tell you that something is probably not actually in production. And I started to kind of hear some of those things and think like, gosh, like, why is it that like people aren't sort of crowing about their production successes? And I think it's because like mostly people were not deploying those models, right? There was a lot of, let's call it experimentation. Maybe somewhat self-indulgent experimentation. I think that those days maybe are behind us. So I think that the key here, the kind of key problem with deployment, a lot of people sort of got excited about the idea of ML ops a couple of years ago, and kind of it sounded like maybe that was going to solve everything finally, magically, somehow. And it doesn't seem like it fully has. And I think that the reason is because when most of us think about what data is in this room, probably most of us picture something tabular, right? So I see some head nods. So when I say tabular, I mean like maybe like a database table, or maybe like a materialized view, like not a true database, but kind of like database-ish. But maybe you're thinking like data frames, right? We had a talk just before this one about data frames. Data frames are tabular, CSV files are tabular. So probably most of us, our culture here of data science, thinks about data in a tabular form. Of course we do, right? Of course we do, because when somebody exports a table to us, sends us a CSV file, finally gives us access to that database table that we've been requesting access for forever, it comes as a table, right? And to add on to that, all of the Python machine learning libraries that we use, all of the Python tools that we use, basically assume that data is either going to be a table or a multidimensional array that is presumed to contain multiple instances, where each instance is a learning example or training example, and each column or each vector position in the multidimensional array is some attribute, right? Something about that instance at that position. But actually, that's not what data really is. It's not tabular. And I think I started to have this recognition when I was talking to platform engineers, and I asked them, how do you think about data? And realized that they think about it in a completely different way from data scientists. And I think that this chasm between sort of that engineering side and data science side, that's the reason why things don't get deployed a lot. And it's because that fundamental mismatch like makes it so hard to deploy a model that's been conceptualized using a tabular paradigm that like it's not even really necessarily always worth it, right? Because the platform engineers know that the data is not arriving in tabular form. And so they're like, this doesn't really even fit into our data system at all. This doesn't fit how data flows into our organization. It doesn't fit how data flows out of our organization. So I asked them, how do you think about data? And they often say things like this. They're asking about, well, do you mean data like in flight or at rest? And they're asking because they're thinking about serialization, right? They're thinking about how am I going to move the data from one place to another, because serialization standards are very strict, right? Because in order to move data between machines, both of those machines need to agree about how we can read the data, right? And so that's extremely strict. There's not a lot of room for interpretation like there is with like CSV files, right? So they're thinking about things like serialization. They're thinking about things like compression, because when you send data along the wire, if you are sending it not compressed, you are rich and you are wasting money, right? So it's expensive to send data that you haven't compressed. And they're also thinking about encryption, right? Because when you are moving data around, if it's in flight, you have to think about encryption differently from how you think about it when it's at rest. Another thing that they ask when I ask them, how do you think about data? They say, well, do you mean raw data or processed data? And the reason that they are asking me that is that it fundamentally determines like how they are going to picture the data that I'm talking about. If I'm talking about raw data, they're thinking about that as like raw event streams, maybe, right? Or maybe SQL dumps, right? Like a table that got dumped, just like a SQL dump, or some kind of like event stream, like Avro. So they're thinking about Avro files that actually store, a series of events from some segment in time. If we're talking about process data, they're going to assume that it's in a different file format, so fundamentally different file format. Maybe something like Parquet, maybe something like JSON. They also are thinking about things like scaling, right? So they're thinking about data in terms of, is it going to make more sense to scale this data vertically or horizontally? So if we're scaling it horizontally, basically that means we're adding more peers. If we're scaling it vertically, it means we're adding more partitions. We're going to break it down. We're going to break the columns down maybe and distribute the columns in partitions. So once you know all of this, you start to get a little bit cocky, and then you say you'll write a book. But actually, before I talk about that, I want to talk about the first model that I ever deployed, because I still feel kind of proud about this, even though it happened kind of a long time ago now. So I'm just going to talk about it a little bit. Basically, what it was maybe like 24 classifiers that we had trained and serialized and stored to S3. That was all done in Python. They were all scikit-learn models. This was the old days. And then there was a Kafka queue that was like the ETL pipeline. So new documents are being delivered on this Kafka queue. We've got a subscriber that's listening to that queue. And when a new document comes through, we're going to use something like a Lambda, right, to wake up the few dozen classifiers. We're going to run all of those classifiers against the document. We're going to export all of the predict proba arrays. And then we're going to add those predict proba arrays as metadata to the document, and then that gets written to Elastic. And then there is, on the kind of the end part, a Clojure web application that renders the data for users, and that metadata that my models have added kind of gets used for cross-tab filtering. And this was a really exciting experience of deploying a model, but it was also really humbling, because I started to learn other things that I just was not thinking about at all. For example, Clojure doesn't know how to speak NumPy, right? It doesn't know NumPy. It can kind of basically understand, generic Python data, but NumPy is not generic. It's got a lot of other stuff going on in there. I also learned that failure is the norm, right? So those kind of peers are going in and out of existence all the time. So when you are doing something like training one of your models, and you know that it's going to be training for a while, you have to think about adding things like checkpoints. You have to think about things like adding exception handling. Like that stuff is not optional anymore. I know that when we're kind of reading from external data APIs, we kind of do a lot of exception handling to say, all right, if I get like a 500 error, then just go to sleep for a bit, and hopefully when I ask again, the server will be turned back on. Or if I get a 400 error, stop asking for, 421 error says, stop annoying me for a little while and take a break, right? All of that exception handling that you use when you pull data from external APIs, you should be doing that on your own internal training code, because the system that you are training your model on top of is not perfect. It is a system that is written with code by regular people on hardware that is going to fail one day, maybe today, maybe tomorrow, right? That sort of failure is happening all the time. So you need to write your machine learning code assuming that that failure could happen right in the middle of a very expensive training cycle, right? So you can kind of start using things like checkpointing. This is an example of checkpointing where you add some kind of checkpointing callback so that every few iterations, the model is dumping the model weights somewhere on disk so that you can then later retrieve those and resume training from that point rather than starting all the way at the beginning. Okay, so I've been thinking a lot about like what is actually my title now. I mean, officially I run a company now, so I just sort of do all the things to keep my business going. But I think that I've started to think about myself a little bit like a use case engineer. So I just made that up. I don't know if anybody else has heard that before. But if they haven't, I invented it. So just tell everybody I invented that. I think I'm a use case engineer. So in my position as a use case engineer, I'm going to give you 5 ideas of things that you could do to make friends with your platform engineering team and start to learn a little bit more about platform engineering in a way that uses the skills that you already have. So here are 5 ideas. Number 1, go to your platform engineering team and offer to build them a custom observability plane from scratch using Prometheus and Grafana. I promise you they already have this ticket in the backlog and they just haven't gotten to it yet because everything's on fire. But they would be so excited if you came to them and you offered to do this, right? And doing it with Prometheus and Grafana means that they can hook up any of the services that they're using, right? Or any new service that they add on later, right? They can add logging to that and it can populate this dashboard later, so you should write it, put it in a repo, give them access, give them control over it so they can add onto it, right? But this is a great way to kind of use your data science visualization skills to build something that is going to help the platform engineering team have insight into like the health metrics and all of those things that they desperately need observability into. Okay, second idea. Build a downtime predictor. So we know failure is the norm. We know things are going to break. It's just expected at this point, right? How expectable is it though? Is it predictable? Does it happen when something happens? Like every time a new client onboards, does everything crash? Is it something that we can learn? Is it something that a model could learn? So I say, see if you can go back and get a data set of historical failure incidents, right? So, see if you can get the system downtime information. See if you can build a model that predicts those historic incidents. And then if you can, maybe just start building like a regular report and sending it to the platform team and see if they're interested, if they think that might be something that might help them. Okay, third idea. Build a resource allocation copilot. Okay, so this is kind of like the idea of like right sizing. I don't know if anybody has ever heard that term, right sizing. It's this, I think, mystical idea that platform engineers have that if they were just like had enough coffee, they could have like the correct number of resources up at all times. So I think that this is probably something that, well, this might be a little bit too hard for traditional models, which is why I suggest maybe looking to reinforcement learning, because resource allocation is pretty complicated. But I think it would be really interesting to try to build a reinforcement learning model that can use something like, maybe some kind of like performance requirements and cost as like the trade-off thing, and see if you can get the reinforcement learning model to optimize those two things for you. And if you can, I think that you'll probably get promoted at your job. Definitely not fired. Here's another idea: build a custom anomaly detector. So there are a lot of anomaly detectors on the market, but they're all super generic because they're trying to sell to everyone, right? So I think that in the same way that we sort of say that domain-specific models are more powerful in a lot of cases than generic models, that's also true on things like log data, right? So see if you can build some sort of anomaly detector to find things that are associated with like security breaches at your organization. It'll be totally in-house. This is something that you can kind of develop as like a skunkworks project, and you might get some momentum. Okay, last idea. Build a language model, or fine-tune, probably, a language model that will produce test data, like synthetic test data. So this is not the same thing as like writing automated tests. This is actually like writing the data that you're gonna push through the system to do some kind of integration test or benchmarking, or maybe a smoke test or something like that. So using LLMs to kind of generate synthetic data, I think is another kind of really cool thing that you can do to catch the attention of the platform engineering team, and also give yourself an opportunity to think more about what the platform team is doing at your organization. And just to kind of sum things up, every time you are doing a query, every time you're training a model, every time you're trying to run a Jupyter Notebook in production, any of those times, and you start to notice something that irritates you more than one time, that is a signal that you have an opportunity to go down the rabbit hole. And you don't have to. But I think that a lot of the things that I hear people talking about are things that I think signal a fundamental curiosity about the platform. And so I guess I'm giving you all permission to get curious and dive into the platform a little bit more, because I think it will help you as a data scientist, and maybe you will be able to help your organization too. Thank you.